We are now moving into acid and base reactions, and you may find that this is a bit odd considering that we just finished up with precipitation reactions, meaning that we took a bunch of ions in solution and we precipitated out some kind of a solid. Now, they are actually pretty similar, acid-base reactions and precipitation reactions, and I'll get into that in just a little bit. So in order to understand how acid-base reactions actually work, you need to understand the basic definition of them. First, an acid is a proton donor, or most compounds that give up an H plus ion. Now, there are other definitions of acids other than this, but this is the most basic and the most widely used one. As you come across other definitions, they really all mean the same as this definition here. So when we're looking at what is an acid, it's anything that starts with an H. So it's HCl, it's HNO3, it's H2SO4, it's HC2H3O2. It's just about anything that starts with an H. In fact, to some extent, it's actually water as well. Now, while we're on the topic of water, let's take a look at the definition of a base. A base is a proton acceptor. Now, there are a lot of proton acceptors out there, Cl minus, NO3 minus, SO4 minus 2, so on and so forth. But we like to consider the most common bases, and those are the ones that end in OH ions. So if you remember back to your solubility rule, there's really only two that have an OH, a hydroxide ion, that are soluble in water, and that's KOH, potassium hydroxide, and NaOH, sodium hydroxide. So why did I say, speaking of water? Well, let's take a look at this formula H2O. What this is really saying is that we have an H bonded to an O bonded to an H. Now, if I separate the bond right here, what do I end up with? I end up with an H plus and an OH minus. So if you take a look at the water structure, water can actually be an acid, meaning that it's a proton donor, or it can be a base, meaning that it's a proton acceptor. And so water is actually one of these interesting, and we know this, that water has all kinds of interesting attributes to it, but it's very interesting in that it can be either an acid or a base, and that's what makes water a bit unique. So we're going to come back to water in just a bit. Let's go on to the next slide here, where we take a look at how we would do some problems that include water. Now this is where you're going to see why these acid-base reactions are in this same chapter as precipitation reactions. So let's take a look at this example. It says, what volume of a 0.1 molar HCl solution, sorry for the typo, is needed to neutralize 25 milliliters of a 0.350 molar NaOH solution? So really, what are you adding together here? You have the reactant of HCl, you have another reactant of NaOH, and now we need to figure out how the products work. So let's write this down. We have HCl, we have NaOH. Now, just as before with the precipitation reactions, we find that H, as a positive ion, will go ahead and bond with OH, and Na, as a positive ion, will bond with the negative Cl minus. So we'll get NaCl, and we'll get HOH. Now, HOH is just a fancy way to write water, remember. But when we do acid-base reactions, sometimes it's useful to continue to write it as HOH so that we are reminded of that dualistic personality where it can also be an acid or a base. So we're going to leave it as HOH. All right, so now we think about our solubility rules. We know that HCl is soluble in water. We know that NaOH is soluble in water. We know that NaCl is soluble in water. But is water soluble in water? Well, that's kind of a difficult one to discuss. But if you think of it this way, does water break apart into ions when it's in water? And the answer to that should be no. And so when you are making water, it's kind of like making a precipitation in a precipitation reaction, a precipitate. It's not a solid, it doesn't come out of solution, but it certainly is a new molecule that stays together and performs a different function than the ions do separately. So how would we write this? We would write this as, by the way, first you should always balance it, but as we can see it's balanced. We would write this as H plus Cl minus plus Na plus OH minus gives us Na plus Cl minus plus HOH. Because remember, water doesn't break apart into ions. So, as we did with our other total ionic and net ionic equations, we need to go through and cancel those things that appear on both sides. In this case, the Na appears on both sides, the Cl appears on both sides, and so we can rewrite this equation as a net ionic equation as H plus OH minus gives you HOH. Now, coincidentally, every single every single reaction involving an acid and a base will give us this type of net ionic equation. Now, the word I was trying to say there earlier is something called a neutralization reaction. Neutralization. Neutralization. That means that you are taking an acid and a base and you're making something that has a pH of 7, or in other words, you're making a solution that isn't acidic or basic. pH, by the way, is something that we don't discuss right now. We'll discuss that once you guys get into AP chemistry if you choose to take that next year or the year after. So keep that in mind. Every single net ionic equation for the neutralization reactions look like this. You're taking the H+, which is the acid part of a ion or of a molecule. You're taking the OH-, which is the basic part of the ionic compound. You put them together, you make water. Water is neither acidic nor basic because it's both. And so you are neutralizing that acid and that base. All right, so how does that pertain to the problem that we have up above? Well, I'm going to change back colors here for a second. All right, it says what volume of a 0.1 molar HCl solution is needed to neutralize 25 milliliters of a 0.350 molar NaOH. Now, just like the precipitation reactions, you need to remember that molarity is a conversion factor. So these two values here are actually conversion factors. They are not going to be our given. So the only value that we are given is 25 milliliters. So that has to be our beginning point. So we're going to start with 25 milliliters. And that is 25 milliliters of what? It's 25 milliliters of NaOH. Now we know in order to start predicting products or other reactants, we need to get to a point where we can compare moles and use mole-to-mole ratios. So the way to do that is to use our molarity. Now, some of you have seen me do this before. Instead of putting 1 liter on the bottom, I put 1,000 milliliters on the bottom because we know that 1,000 milliliters and a liter are the same. And then we can use the 0.35 moles of NaOH on top. And now you should start seeing why labeling which compound we're talking about is so important. Now, if we want to get from NaOH, we're trying to get to HCl. So if we want to get from NaOH to HCl, we need to be able to do a mole-to-mole ratio. If we take a look at our first equation, it's a 1-to-1 ratio. Or if we take a look at our net ionic equation, it's a 1-to-1 ratio. So it's 1 mole of NaOH to 1 mole of HCl. Now we could stop there if they asked us for the number of moles, but they're asking for the volume. So now we can use the molarity as a conversion factor. We know that for every 0.1 moles of HCl, the volume that is in is 1,000 milliliters. And so if we cancel all of our units out, milliliters, moles, 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 we are left with milliliters of HCl. Now I apologize, my stylus doesn't seem to be working really well. All right, so hopefully you'll notice right off the bat that the 1,000 milliliters, the one on top and the one on the bottom, actually cancel out pretty readily. So we're going to take 25 times 0.35 and divide it by 0.1. And you'll find that it takes 87.5 milliliters of HCl to neutralize 25 milliliters of that 0.35 molar NaOH. All right, let's take a look at another example here. Notice, and maybe I should have mentioned this earlier when we were talking about precipitation reactions, but notice that I do not usually use the net ionic equations, and there are some professors and teachers that swear by those. I like to stick with the original normal molecular equation that shows us what's going on, the ones that we balanced originally. But some of you may feel more comfortable, and as we get into more ions and things like that, you may need to actually become more comfortable with those net ionic equations. But for now, you could go ahead and use the molecular equation. All right, let's take a look at the next one. It says, in a certain experiment, 28 milliliters of 0.250 molar HNO3 and 53 milliliters of 0.320 milliliters, whoa, hello, that is not supposed to be a milliliter there, molar KOH are mixed. Calculate the amount of water formed in the resulting reaction. What is the concentration of H plus or OH minus ions in excess after the reaction goes to completion? I'm actually going to take a pause here and start a new video to show you this one because it's going to take us a little more than the minute or two that I have left on this video. So stay tuned and go ahead and click on the next video.